many solvent molecules that act as the rest of the universe, and this thing that has sufficiently high energy and sufficiently many degrees of freedom that I can treat it as a heat reservoir. So part of the reason for showing you these particular methods I want to talk about is that I can take this function, which is basically my first NODI Monte Carlo sampler for physicists. It's going to implement Markov chain Monte Carlo, and I'm going to make a random move in a random direction. I'm going to accept or reject it according to the Metropolis criteria. As I go along, I'm going to show you what changes I need to make to this to implement these more advanced methods that we actually use on a day-to-day basis. And in most cases, it's about 4 lines of code that we have to add. It's very simple modifications.
And now you're only changing one beat.
I'm only changing one beat at a time. Yeah, so I'll just sort of flip through the code. So I'm taking in a temperature, I'm defining my inverse temperature. I'm going to build up a list of samples. I'm picking a random bead. Okay, so this is my making sure I have detailed balance. If I worked sequentially through the beads, I wouldn't have detailed balance, okay, because the probability of attempting the reverse move at the next step would be 0, because the next move operates on a different bead. So I have to choose my bead randomly. Generating a random displacement, so just a random displacement in X, a random displacement in Y, up to some maximum displacement in each direction I'm calling max disp. And then this is the function that computes just the contribution to the energy that involves the randomly selected bead. I then make the move, I recompute that energy contribution, and then compute the change in energy, accept or reject it according to the Metropolis criteria. If I reject it, I put the bead back where it was. And then I'm at some interval, I'm storing samples of things I might care about, I might want to compute expectations of in this system. So one of those is going to be the energy. I'm always interested in the energy. And for the purposes of what comes later, I need to show how I can compute expectations in various algorithms of things that aren't the energy. And just to pick something that's relevant to the system, the thing I'm going to compute is the end-to-end distance. So there's the straight Cartesian distance between the first bead and the last bead on the chain. I'm doing that at intervals. And the reason for that is I always need to subsample my Markov chain in order to make sure that I'm not drawing conclusions from correlated data. I don't know in advance what the autocorrelation time of this chain is going to be. I don't know how often I can subsample, but I'm going to use some physics and some experience to tell me that. What have I set that to by default? I've set that to 100 samples. I know it's going to be at least 100 samples, so there's no point sampling at an interval that's finer than that, because I'm just going to end up throwing that away when I subsample. A bit of lingo, just so that I don't say words that mean nothing. We tend to use the word sweep. So a sweep is a number of trials that on average attempts to move every degree of freedom once. We tend to measure how many trials we've done, how many steps on our Markov chain we've done in sweeps, because it gives us a nice scale-independent way of measuring how much sampling we've done. So if my system gets bigger, if my chain gets longer, if I change the number of beads, but I keep the number of sweeps the same, then I'm doing correspondingly more Monte Carlo trials. So it's number of trials per degree of freedom is a sweep, essentially. Okay, so if I define that function, so I do like a progress bar. What I've done is I've set that running. Where's my picture? There's my picture. So each one of the frames in this animation is, I think, I'd have to scroll down and see it. It's some number of sweeps, 100 sweeps. So it's every 100 Monte Carlo moves, on average, 100 moves per degree of freedom. I'm showing a frame in this animation. Okay, and it wobbles about and samples various configurations. I'm running this at a particular temperature. I forget what temperature I'm running it at. 0.4. Yeah. So that's nearly finished. Yeah, so all I'm doing is for every frame in the animation, I've done 1,000 frames, run my MCMC routine with a maximum displacement of 0.1, arbitrary distance units that don't really matter, at this temperature, accumulating the samples and updating the plot. Yep. Why? Physics is translationally invariant. So all I do if I let the first bead move is I'm just moving my origin, and that doesn't tell me anything interesting. So. Yes.
So in this type of a problem, I guess this is a toy problem, but
it's a toy problem.
What would a representative scale be like for maybe a medium, hard, or difficult? Right, so 7 beads seems like sort of a small scale somehow.
Oh yeah. I mean that's trivial. Yeah. So we have done. So give you an example of the kind of thing you might be interested in is this being a toy model or even a more detailed atomistic model where we might have a chain of hundreds or thousands of atoms, or probably more frequently, we're using some kind of coarse grain model where each bead on the chain represents an amino acid on a much longer biopolymer. So it might be representative of tens of thousands of actual atoms, and we're looking to understand the temperature at which there's a transition in the behavior of the polymer. We also look at polymer melts on occasion, so we've got not just one chain but many chains, and then that makes things much more complicated. That's also a much harder sampling problem as well. I probably won't get into the kind of methods we use to deal with that. So yeah, this is on the scale of a real calculation. This is trivial. Okay, so I just wanted to say a couple of things that are going to become important about the configurations of this polymer. It has a ground state. So if that's my fixed bead, and I think about a hexagon, then I might have, okay, my first bead, and then the rest of the polymer wraps around it. And that's a very low energy configuration because all of my springs, all of my bonded interactions are at the right length and they're happy. And the non-bonded interactions are also at about the right length. They're sitting at the minimum of that energy function and they're happy. So that's a very low energy configuration. This is also quite low energy. So I've got something that's nearly a hexagon, but this guy's just flapping around. But the interesting thing for what's going to come later, what's the pathology in this system, is, well, that's a low energy configuration. But I could also, that is also a low energy configuration with a very similar energy. Okay, I've got a slightly different, I've just changed the identity of which bead is which. And transitioning from that first configuration to this configuration is something that's never going to happen in a million years with these single particle moves. So that's going to cause me a problem if I'm only sampling at very low temperature where very low energies are accessible. Okay, so where am I at in my little sheet? Let's just plot some things to make sure that I've got nothing up the sleeves. No, that's not what I want. There we go. So this is my energy as a function of sample. It's my end-to-end distance as a function of sample. You can see some hints of metastability here, that I've got some state that I like to live in for a relatively long time, which is basically one of these. It's the collapsed state. So we call that a collapsed state of the polymer, a coil. And then there's some more expanded state, but it's obviously a bit less stable at this particular temperature. And we call that the globule. Okay, so it's coil globule. Okay, so what might I want to calculate to characterize this system? And I'm going to focus on three things. I'm going to focus on the energy histogram. So this is the histogram of energy samples that I generated during that run that we just did live. Okay, fine. Doesn't look like there's any problems with that. The temperature of 0.4. What I said I'm interested in is trends with temperature. I want to understand the behavior of this system as the temperature increases or decreases. So in this sort of very simple way that Michael laid out on Monday, I just go away and I do this at many different temperatures. So I run many simulations at a series of temperatures I'm not going to do that live because it'll take a while. And what I want to do is to run for some extreme lengths to show you that even if I run for as long as I can be bothered to run, I'm not going to get good answers in this case. So what I'm doing here is I'm looping over a whole bunch of temperatures from 0.1 to 0.5. I'm running for 50,000 frames. So that's 50,000 times 100 sweeps. So I'm not going to run that live. I'm going to load these from a file. So I'm loading the data from a file. Here's one I did earlier. And what I'm going to work out is the mean energy at each temperature. So the mean value of U, the expectation of U, okay, which in Python is an easy thing. I'm computing this from the samples. So I've stored every 100 trials a sample of the energy in the end-to-end distance. So I'm computing the mean of the samples. I'm computing this thing called the histogram, sorry, the heat capacity that Michael ducked a bit on Monday, but I can't do that, unfortunately. I'm going to have to explain what a heat capacity is. So the heat capacity is the derivative of the mean energy with respect to temperature. So it's telling me how much energy I need to raise the temperature of my system. And as I approach a phase transition, as Michael showed us, that will behave in an analytic way. If I'm in a bulk infinite system in the thermodynamic limit, I'm not. I've got a genuinely finite system. But if I've got some kind of transition in that finite system, I'll see a maximum in the heat capacity. So that's the thing I'm looking for. And the heat capacity we compute as it's some function of the variance of those energy samples. In fact, it's the variance divided by the temperature squared. And then this bit on the end, referring back to the kinetic energy, is the bit that I can calculate analytically that the kinetic energy makes to the contribution the kinetic energy makes to the heat capacity. And that's just a pen and paper exercise, and it results in that term on the end. So if I run this, I should get 3 plots. So what you're seeing is from each of these individual simulations, 0.1 up to 0.5, that's the energy histogram that I got from running that single simulation. This is my best estimate of mean versus temperature. I've been a bit naughty here. I talked about properly subsampling my data so that I could compute the standard error. What's the uncertainty in the estimate of what's the uncertainty in my expectation of the energy? I couldn't be bothered with that, so I haven't put the error bars on. And then here's the heat capacity. And something's gone wrong here. So there is a peak in the heat capacity, which is indicating to me there's some transition from this, what did I call it, a coil to the globule as I increase temperature. This is nonsense. That shouldn't be there. Something's gone wrong. And that's a result of this pathology. So if I run a simulation at a temperature of 0.1, it might say access this state, which has close to the minimum energy of the system. And it might spend some time accessing this state where one of these guys flaps around a bit. So I'm going to get in my histogram of the potential energy, I'll get a spike down here, and I might get a little spike up here, which corresponds to this flapping around. But there are many other ways that I can draw the bonds between to populate this hexagon, this low energy hexagon, that would fill out this gap in between. So I'm actually overestimating the variance in the energy here because I'm sampling one of the low energy states and something that's a bit higher energy, but I'm missing out lots of states in between that I can't get to because of this non-ergodic trap. There is no way for the system to transition between this set of bonds forming the hexagon and some other set of bonds forming the hexagon without going via a higher energy state. And if I'm doing a single simulation at a low temperature, the probability of sampling those is basically 0. So I'm never going to get between different configurations of this coil. Yep. Because the variance of this is larger than the variance of that. Yep. If I'd filled in the gaps and I had these, if I'd sampled everything properly, then that variance would be smaller than if I don't have the ones in the middle. And the heat capacity is the variance in the energy to within factor of 1 over temperature squared. Yeah. So if you work out, if you write down the expression for the expectation of the energy, you differentiate it with respect to temperature, what comes out is the variance of the energy, basically. Yeah. So that's one thing. I've got this pathology that means my low temperature sampling is rubbish. Please.
So at low temperature, I would expect that if you have a multimodal system, then these modes they will grow to infinity, and whatever is not a mode will just shrink to 0. So having a gap between the two energies.
So if I was to try and draw another axis coming out of here that was an order parameter that was somehow distinguishing between the different ways of coiling, then what I'd see is there are multiple minima, but they're not all at the same energy. They're at slightly different energies because they're all balancing the non-bonded and the bonded interactions in slightly different ways. That's not something I've actually done to show you, but that's what will go on. So the modality is out of it's orthogonal to the direction of the energy, if you like. So I don't want to give the impression that this is somehow an incredibly difficult problem that physicists haven't got the answer to. So I'm just making single particle moves. I could make a move where I say, okay, I'm going to break this bond, and no, that's a bad example. A move where I break this bond and I form this bond instead. Now I've got some disjointed thing, so I might need to make that bond and break that bond. And now I've moved into a different configuration of that coiled polymer. So there are people who work with bond breaking and forming moves to get around exactly this kind of pathology. But doing those in a way that obeys detailed balance is quite difficult. Incidentally, in this context, there's something called the dancing links algorithm. I don't know if people have heard of that, or algorithm X, which is a contribution to this field from Donald Knuth, of LaTeX fame. So it's a fun thing to play with. The other thing I could do to try and solve this problem, what I've done here is multiple independent simulations at different temperatures. And I gather from talking to some of you during the week that parallel tempering is a thing in your field. So I could, rather than having 1, 2, 3, 4, 5, 6, 7, how many simulations I've got running completely independently, that could be one parallel simulation where I'm exchanging configurations between adjacent temperatures on that temperature ladder, accepting or rejecting them. And then that gives these configurations access to information about higher temperatures that can move back down and access ways of moving between these other configurations. Now I'm going to say, don't do that. I'm going to try and convince you that what you want to do is not that. What you want to do is one simulation that accesses the entire energy range from which I can get information about multiple temperatures in one go. So this is this idea of multi-canonical sampling. What we've done here is canonical sampling. So we call the distribution where the probability is the Boltzmann factor. That's the canonical ensemble, the canonical distribution of configurations. Hence, multi-canonical means one simulation that's going to get me information about the canonical ensemble at many temperatures, at multi-temperatures. And I'll say a bit about why that might be more advantageous than a parallel tempering type approach. Okay, so just making sure I've covered everything that's in my notes here. Other reasons I might not want to do this is, okay, I've got discrete temperatures at which I have simulation data. I might want to be able to have continuous temperature data, and I can get that from multi-canonical sampling. If I've got samples across the entire energy range, I can reweigh those samples to give me information about any temperature, at least in principle. And then the other comment is about efficiency. But here, these histograms overlap quite a lot. So I've got one of the processes in my parallel tempering is spending a lot of time. I should say that in all of these kinds of simulations, the computational expense is in evaluating U. So when you make a move and you need to know how has U changed, that's the expensive bit, right? That's where 99.9% of your CPU time is spent. So if I'm spending time generating samples that have an energy here, and I'm generating basically the same samples on another processor for the purposes of doing parallel tempering, then I'm wasting computer time if there's a better way of doing that. So that's another one of the motivations. And then finally, this is a toy problem with 6 mobile beads. As I go to larger and larger numbers of beads, or larger numbers of degrees of freedom in my system, these histograms get narrower and narrower. And so in order to have overlap between adjacent histograms on a parallel tempering ladder, I need to have more and more steps on the ladder, which then becomes more and more expensive very quickly. And multi-canonical sampling doesn't suffer from that. Okay, so that's kind of the noddy way of doing it, and what I'm saying is potentially wrong with that, and why we don't do that, or why I don't do that. Are there any questions at that point? Yeah.
That when you make this simulation, very hard to see whether a big at 0.1 is curious or whether it's something you can real. So
yeah, if I was going into this completely blind, yeah, I might be trying to attribute physics to that. Yeah.
I wonder whether if you repeat that simulation multiple times, and
yeah.
then if you like create the confidence interval for each one of the dog, then you may have to.
Yeah, so I could run many simulations with different initial conditions at a temperature of 0.1, add all the statistics together, and yeah, hopefully I'd see something that was very different to this spiky mess. I'd get something smooth, but then I'd have to run many simulations. Right. Any other questions on the basic approach? Good, right. Just checking there's nothing else that I wanted to say there. So this Teams bar is annoying. I'm going to have to move down and then back up again. Oh yes, another thing I should mention, just to be fair to Livia, is this energy histogram. When I defined my model, why did I do that? There we go. I skipped over this, and that was a bit rude. I said, I'm interested in the energy range from -6.1 to +4 energy units. How did I know that that's the energy range that I'm interested in? Okay, so in practice, what I'd have to do there is I'd have to run a simulation, a standard single temperature canonical simulation at the lowest temperature I care about and the highest temperature I care about. And then I would look for the minimum at the low temperature and the maximum at the high temperature and say, okay, that's the energy range I care about. The method that Livia is going to talk about this afternoon doesn't care about that. It just does it. Okay, so that's, I'm giving you a leg up there, Livia, that you can, it's one advantage of nested sampling at least over what I'm talking about. Okay, so multi-canonical sampling, how do we do it? So this was actually hinted at yesterday. So I think Pierre said yesterday that the method he was talking about, ABF, of essentially picking a collective variable, a low-dimensional description of the system, and coming up with a way of biasing that collective variable so that I get broad sampling across a broad range of that collective variable, much broader than I would get if I just ran a simulation at a single temperature where it would be stuck in some local minimum, especially if I was bimodal. If I just ran a standard simulation, I'd be stuck in one of the modes. But I can come up with some collective variable that I bias that traverses these modes and get good sampling that way. And I mentioned that if you choose that collective variable to be the energy, then what you're doing is multi-canonical sampling. Okay? You're coming up with a way of sampling a much broader energy range than you would sample if you just ran a single canonical simulation. So that's exactly what we're going to do. We're not going to do anything like a sophisticated or as clever a way of generating the bias. I'm going to do it in the dumbest way possible, just for the purpose of a demonstration. So the idea of multi-canonical sampling, it's an old method, dates back to 1992. What we're looking for is we're looking for a flat histogram in the energy. So over that energy range that I've decided I care about, I want to sample all energies with equal probability. And then because I know the magic of the Boltzmann distribution, I know how the statistical weight of any sample depends on the energy. I can just take the samples that I've generated from that flat histogram, assign them that statistical weight, and then compute the histogram that I want at the temperature that I care about. And I can also do that for other quantities that aren't the energy, but there's an extra step that I'll come to. So just to again make sure I'm getting my language straight. Microstate means all of the positions in the system. So a microstate is a configuration of the polymer, where poly means 7. And macrostate, in this case, I'm going to talk about an energy macrostate. So I've divided up my energy range into a series of discrete bins. Each one of those bins is an energy macrostate. And I'm looking for a uniform sampling of energy macrostates. I will sample all energies with equal probability. So the probability of visiting a particular energy macrostate, in the canonical ensemble is just given by the Boltzmann factor multiplied by the number of microstates that exist within that energy macrostate. So how many configurations of the polymer are they that have the energy within that energy macrostate, within that energy bin? So I'll call that the density of states, and that's G as a function of U. And then the partition function is the normalization. In one of the methods we'll look at a bit later on this morning, the G is going to be a lot more important than it is here. We're going to do everything in terms of G a bit later on.
So G of U is quite related to what Pierre was calling the free energy.
It is, yes, yeah. So G of U, if I measure G of U on a logarithmic scale, then it's the Boltzmann entropy. I think we got to Wednesday afternoon before the word entropy was used in any of the talks, which surprised me a bit, but I guess that's just not the lingo in this community. And then what Pierre called the free energy is this thing I'm calling A of U minus KT log P of U. So there's a contribution to that from G of E, which is the entropy minus T times S, contribute to the free energy, and there's a contribution to that from the Boltzmann factor of that energy macrostate. So if I want a flat histogram, so these multi-canonical methods are sometimes called flat histogram methods. I want to visit all energy macrostates with equal probability, then I know how to do that. I can add an extra energy on top of U that I'm going to call V as a function of U, such that I get uniform sampling. And if I choose that V of U to be KT log P, where P is given by this expression above, then everything cancels. So I'm calling P tilde. P tilde is going to be the distribution that I get in the biased simulation, which has got this extra V of U on top of the energy. If I happen to choose V of U is KT log P, then everything cancels, and P tilde of U is just 1. So within some normalization constant, I'll sample all the energies with equal probability. The obvious problem there is that P of U is the thing I'm trying to find. So if I knew it already, I could construct the perfect bias potential to give me a flat histogram and a uniform sampling in energy. But I don't know what it is. So I'm going to have to come up with some iterative procedure where I guess an initial P of U. I run a simulation. I find what is the P tilde of U for that guess of V of U. That will get me some new distribution P tilde of mu. I can invert that. So this procedure is called Boltzmann inversion, of where I take this probability P tilde of U. So I'll put P tilde of U in here to get a new bias potential, and I'll iterate until that bias potential stops changing. Or in practical terms, actually, I don't really care about having a perfectly flat histogram. I just want a histogram that gets me good statistics everywhere in the energy range that I care about. It doesn't have to be flat. It just has to be, well sampled everywhere. So there are various increasingly sophisticated and clever ways that you can do that you can come up with that you can iteratively refine an estimate of the weights. I shouldn't call them weights, I should call it a bias, V of U, to push me towards a broad sampling across the full energy range. So yeah, this is the procedure. I'm going to set my bias to be 0. If I have some, I'll use the loaded term. If I had some prior expectation of what I think V of U should be, I could put it in there. I could use that as the bias weights, run a Monte Carlo simulation, sorry, as the bias function, run a Monte Carlo simulation with that as the function. What is the probability distribution I get from that? Invert that to get new weights and iterate. Please.
If I understand. Beta here, the temperature is not fixed, right?
So I'm going to pick very good point. I'm going to pick one temperature at which to do this. So I'm going to pick a temperature. So I'm doing a canonical simulation in that sense. There is a temperature, but I'm biasing it to go everywhere at that temperature.
Okay.
That'll get me all the information I need to say things about other temperatures as well. Okay, so there is a fixed temperature in the simulation.
And how do you pick the temperature?
Doesn't matter. It could be anything really. Any temperature that is relevant to the energy range will work. Yep. Yes. Yeah. So I'm finding the V of U that gives me a flat histogram at this temperature. Yeah. But then that will get me information that I need that's relevant to other temperatures as well. Probably, but that's probably not what I would call it. So Pierre yesterday did talk about reweighting, so that he could look at, he was computing a distribution across some collective coordinates, and then he was reweighting that to, I'm not sure if it was other temperatures, but to other hyperparameters. Yeah, if that's what you would call an important sampling curve, yeah, that's what we're going to do. Yeah. Okay, so I'll demonstrate that. Maybe that'll take 5-10 minutes, and then maybe we can break for a coffee, and I'll move on to one of the more sophisticated methods. So I'm again defining exactly the same functions that I defined earlier to create the polymer and set up the bins and so on. I feel like I should explain that comment where I said I'm aware that numpy.digitize is a thing, but I don't like it. For some reason, some of you are Python programmers, the way that numpy.histogram breaks up the energy space is incompatible with the way that numpy.digitize assigns samples into bins. There's a difference of 1 bin. And I could not find a way to make them, I gave up. And I said, right, I'm writing my own function to do the binning. The other thing that scared me actually, as the guy who has to buy the computers that people waste time on, the implementation of digitize in NumPy takes the bin edges, sorts them, and then loops over them until it finds the bin edges that are either side of the sample. And we teach the first year undergraduates that's the stupid way to put samples into bins, right? You do it like this, it's much faster. So if you happen to know any of the NumPy developers, then pass that on. Okay, so this is a function that's going to be key to the procedure. So given a set of energy samples that I've generated that are distributed according to P tilde in my biased simulation, give me back the histogram, give me back P of U that is unbiased at some other temperature, which may be the same temperature I ran at if I'm interested in that as well. So that's very simple, is I'm just creating a set of weights, one for every sample. I'm looping over the energy samples, which bin am I in? And then the weight for that sample is I'm just doing exactly what Pierre showed how to do yesterday, is I'm multiplying by the Boltzmann factor that I want, which is this, and I'm dividing by, I'm multiplying by the weight that I want, and I'm dividing by the weight that I have in that biased ensemble. So that's giving me how much should I count each sample when I build a histogram, such that I get an unbiased histogram at whatever temperature I've told it to compute it for. So it's really trivial. It's just what weights have I got? What weights do I want? Divide one by the other. And then one thing I learned that I didn't know is that NumPy will do that for you as well. You can just build me a histogram, but count each sample with a weight that isn't 1. I didn't know NumPy would do that, but apparently it does. It does that bit right. Okay, and then as advertised, this is the code that then implements the Markov chain in that biased simulation that will eventually, hopefully, get me to a flat histogram. So just again, to highlight that I have to change very little. And this is sort of me talking to my graduate students, right? Where's Hubert? Yeah, it's very little effort, Hubert. It won't take you long at all to take a Monte Carlo code that, say, your office mate has written and to add something like this on top of it. So the only thing that I'm changing up here is before, when I did the Monte Carlo, I only needed to know, I only cared about the energy contribution made by the bead that I was moving. But here I need to know what the total energy is so that I can put the samples in the right bin and that I can compute the bias function from the total energy. So I'm just keeping track of the total energy. So what is the old energy? I do exactly the same move, only now I have to decide which bin was I in, which energy macro state was I in before I made the move, which energy macro state am I in after I make the move, and then I compute the old bias, the new bias, and I add that change in bias to the change in energy. And then that's what I use for my Metropolis criteria to accept or reject the move. So that's what 4 lines of code different from the previous version. Okay, so same polymer, same energy range. My plots are going to be slightly more sophisticated now. Come back to that in a moment. And then I'm going to call that function that does 100 sweeps, MC sweeps in that biased ensemble many times to create an animation and refine the weights. So I'm looping over the number of frames in my animation. I'm running some number of Monte Carlo sweeps. And then periodically, once per frame in the, oh no, sorry, I'm now defining cycles as well as frames. So each cycle is going to be a certain number of frames. A frame is a certain number of sweeps. A cycle, once per cycle, I take my p tilde histogram, the histogram I've generated in the biased ensemble, and I construct from that a new set of weights, and then continue. So I'm only going to do 5 cycles. So that's the outer loop is over cycles. After I've done with the inner loop, I call I say these are the energy samples I've generated in that biased ensemble. Give me back the histogram that would be unbiased at this temperature. And then I'm going to, this is the Boltzmann inversion step. This is creating the new bias function from that p tilde. So that's the KT log p step. A couple of wrinkles in there that I can have all kinds of divide by zeros and other things I don't like if I'm trying to build these weights for energies that I haven't visited at all yet. I'll get numerical errors there. So I go through my histogram and I say, if there's anywhere I haven't visited at all, that so far I think has a 0 probability, I increase that to the minimum probability across all of the bins that I have visited. And that step won't make any difference once things converge. But initially, it'll stop me from having divide by 0 errors. So if I set that going, so this is currently an unbiased simulation because my weights are 0, and I'm just building up the histogram that's relevant to the temperature I'm currently simulating, which is a temperature of 0.4. And then in a moment, you'll see a jump in that bias, which is the first time it iterates through that loop and creates a new V of U. Yep.
When you, the thing you just said, when you elevate the probability in a bin where you get the responsible energy you haven't visited yet,
yeah,
filling gaps in the histogram, right?
Exactly. Yeah.
Beyond the sort of visited data.
It is. So if I took this histogram as it is, for example, and I said that's the minimum, I just raise everything to that minimum across the full energy range, which means that the first iteration. Exactly, yeah. And once I get a good set of weights that get me sampling everywhere, that step won't do anything. But it does mean that my first few estimates of the weight will have artifacts in them. I've set this to run for 5 cycles. That might have been too many. I do have a progress bar somewhere, but you can guarantee that as soon as I scroll down to look at the progress bar, the interesting thing will happen. So. Yeah, so far what you're looking at is just a standard MCMC simulation because there is no bias. I could have, again, used some prior knowledge of what I think the free energy is to construct something. So now I've got something that's quite noisy. I'm now using that as the bias, which is going to push me away from regions in the middle and towards regions at the edges where the bias is lower. So you'll see that histogram is now much broader. So I think the intelligent thing to do here is to have a 10-minute break while that runs, and then we can use the actual data that is being generated live rather than here's one I made earlier. So 1/2 or 25 past, whenever people are ready. And if you have questions, then feel free. Yeah, 1/2.
There are coffee machines.
There is, but there's also a kitty.
Okay. But I got access to the video.
What, you mean to next door? Or?
I don't know, I could enter here.
You got into the building?
Yeah.
Yeah, there's no coffee machine in the building other than the one that's in the common room locked behind a code. I mean, the code is 5022, but there's a kitty you're supposed to pay into for the coffee. But there's a water fountain next door as well if people want to use that, so 5022 to get in.
We tell people that.
Sorry? Yeah, why not? Yeah. We trust statisticians. Yeah, so it's 5022.
Yeah. Can I ask you
yeah, please.
something? Because I had to go collect something
okay.
outside. So basically, I remember we got to the part where you said you have this configuration,
Yeah.
and then it's difficult to get that into a completely different configuration because then you have to cross a higher energy.
Well, to a configuration that's also a coiled hexagon, but with the bonds in different places.
Yes, exactly.
Yeah.
Exactly. But then I missed.
You missed the green bit.
How do you go from one to the other using because you use the bias to sort of be able to cross these barriers.
So what the bias is giving me is, I mean, if you look at the walk, right, what the random walk is doing is going up and down the entire energy range. Mm-hmm. So if I'm stuck in this configuration, I can get to the other configurations if I've got access to higher energy configurations.
Yes.
And the low temperature, I don't. At a single low temperature, the probability of sampling a high energy configuration that will allow me to expand and then recoil differently is never going to be sampled in a million years. But because I'm now biasing all energy, I'm biasing to get sampling across the full energy range, a single MCMC chain is going to be coiled, expand, recoil, expand, recoil, and I'm going to visit lots of different coiled configurations in one simulation.
Okay, but so I missed the formulas. Practically, I think you add a term to the energy.
Yeah.
And that,
So this term. So if I was to run,
this is the V of U or something.
this is the V of U. Yeah. So if I was doing this at low temperature, I'm doing this at temperature 0.4. If I was at 0.1, where I have this problem, this bias would be much more concentrated here, and it would be pushing me away from the low energy configurations into the higher energy configurations.
Okay.
And then to come back to make the histogram flat, I'd have to recoil. I'd have to coil up again. And I might coil now into something that's a different way of coiling around an atom on the chain to make a hexagon. So I can get between these otherwise disconnected configurations.
To me, this feels like essentially the same sort of action that parallel tempering has.
Yeah. It's parallel tempering, but in one simulation, basically. Yeah.
With simulated tempering?
Define simulated tempering.
So you're not changing the temperature.
I've got one temperature, yeah.
Yeah, but maybe the effect is similar to when simulated tempering is when you change the temp. You let the temperature be an extra parameter.
Yeah.
Right? So it's very parallel tempering.
So I would move the temperature up and down according to some schedule. Yeah, okay.
Within a temperature you explore.
So the difference there
Change the temperature.
is what I'm heading to here is, as we discussed, I'm going to be able to reweight these results and get information about every temperature. Whereas if I've got a temperature that's changing on a schedule, then each sample that I'm generating is being generated at a different temperature. And I can't do that reweighting as easily, I think. So I don't know.
And that's only simulated tempering, right? Because for parallel, no.
Well, simulated and parallel tempering, the only difference is that parallel tempering, you have one chain running at each different temperature, and you will attempt to exchange positions, let's say.
So simulated tempering is...
You say, I'm at a current temperature, I'm going to explore a bit this temperature, and now I'm going to propose to change the temperature.
Yeah.
But you've got a single change.
So I guess if you...
Once you change, do you go back?
Yeah, you can then go back to the other temperature, and you can forward. You can have, let's say, the same schedule.
Yeah, so we would call that simulated annealing, I guess, is what we call
Okay.
it.
Well,
for simulated annealing, we'd probably bring the temperature down to find the minimum, and we wouldn't go back up. Yeah. So I guess you're saying we pump the temperature basically up and down. So yeah, if you
the Marinelli Parisi.
maybe, yeah. So I guess you could do everything that I'm going to do here with simulated tempering if you hold at each temperature long enough to build up a probability distribution out of that temperature.
Yeah, exactly.
Yeah,
So
yeah.
if you say, I've already explored each of my scheduled temperatures,
Yeah.
and I have a proper exploration of the energy at that one, then you could use, who asked about important samples?
Yeah.
You could have like the broadest,
Yeah, you could.
or if
I think
you're
that would work,
interested in
yeah.
a temperature within two of your schedules, right? I'm guessing the broadest one can serve as the what we would call an importance distribution to weight, right? So I'm still trying to see why with tempering you would not.
I think it would work. I think it's another thing you could do that would be just as good. Yeah.
Okay, and there's no study comparing these things.
Maybe.
Okay, so now I know what to do.
Yeah.
This would be really useful. Like there must be.
Where's Christian and well, maybe Garrett's listening.
So I'll say a bit more when we get into some of the methods, but a lot of these methods are all variations on a theme, and different groups have their own implementation and their own tweaks to it, and lots of people get very het up about, my variation on this theme is better than your. I don't care. I'm a user of these methods. I have no skin in the game. I just use the one that works for me.
But yeah, that kind of, because here important then is, and that's what you mentioned about previous work, right? You need to know, you're interested in the evolution. Sorry, because I arrived a little bit later.
Yeah.
There was accident from the way Leamington to here.
Oh, really?
So we were stuck on the bus for probably 25 minutes.
Ouch.
So you are interested in the behavior of the system through a range of temperatures, right?
Yeah.
You're not interested, like as before, people were interested in one single temperature, and that was the canonical one. Whereas here you want to see the evolution as the temperature changes, and you want literally all the possible temperatures.
Yes, I want a way of give me one simulation from which I can extract information about any temperature. Yeah.
Now, but you would need to know beforehand the whole range of energy that you would be interested in, right? Which is, for us, if we think of the states as X, you need to know across all the temperatures how little and how far.
Which in practice it's a limitation, but in practice it's a pretty trivial limitation because you can just say, what's the lowest temperature I care about? Run a quick simulation, get a histogram. What's the highest temperature I care about? Run a quick simulation, get a histogram. And then look at a minimum of one, maximum of another, and there's your energy range.
Yeah, now I'm very interested. I want to see a comparison.
But also, like, maybe there are models and situations where one works better or you can't do one and not the other. And,
But I should also say this isn't what I do. I'm going to go through more sophisticated methods that work better.
How do you choose the partition of the energy space once you've just decided on which range of energies that you want to use?
Good question. I guess it's the resolution that you need, really. So you can, what I'm ultimately looking for is I'm trying to find the peak in the heat capacity. And the resolution of where I identify that peak is going to depend on the energy range, on the width of that bin.
But whether you achieve whether you or how fast you like do the reset will depend on the particular partition of the energy that you're using. Right?
Yeah. So if I had very narrow bins, then I have to wait longer to make sure that I haven't got any holes in the sample space.
And you would always use an evenly spaced partition of the energy.
No, I do it in an oddie example, but the stuff that we do in anger, we might be dealing with a function like this that is has a very sharp minima, and so we'll have a finer grid of energy in there and a less fine further out. And then you have to adjust for the width of the bin when you're calculating probabilities and so on.
It's related to the spacing of the temperatures as well, right? Whenever you have that peak of you need more temperatures, need the heat capacity.
And some people don't use bins at all. They use a kernel density estimate to build a smooth.
So on this exactly, because I'm coding something up with the parallel tempering, and obviously the temperature schedule is different for every problem.
Yeah.
And I was like making up practical ways of finding where the transitions, the transitions of the system between states occur, and sort of want to put more temperature. Like in physics, there must be other concepts or like quantities you can calculate to sort of advise, because I do this by eye.
Well, okay, so I need my histograms to overlap. Okay. The width of the histogram is the heat capacity.
Okay.
So if I have some prior knowledge of how I expect the heat capacity to change as a function of temperature, then I could come up with an optimal spacing. But normally that's the thing I'm trying to calculate. So I don't know. In practice you end up going, oh damn it, I've got no samples in that energy range. I need to put in another replica.
Like Seth what it does. So Seth has an algorithm to do that, which is sort of saying, I'm going to try to have as many temperatures as I can, and you iteratively try to see change, because you know how much you want to exchange between temperatures. Right? There's an acceptance rate.
There's an optimal acceptance rate.
Yeah.
So that's the thing I meant to mention and forgot actually, is I could have taken my independent simulations and pieced them together to give me something that was over the full energy range using what I would call MBAR. Modified multi-state Bennett acceptance ratio. So you just pick samples from your histogram and say, well, what would the probability, what's the ratio of Boltzmann factors in this histogram and at the other temperature? You do that over many samples, you get the average probability of moving from one temperature to the other. That tells you how much to shift or multiply one probability by to match the other at the boundary, and you can do it that way. But you're still, you're wasting time generating samples in the overlap region.
Yeah. In a way. Yeah, exactly. That's the problem, right? If you don't know, and that's the big problem. You would like to know the heat capacity beforehand. So you would know where to put the temperature so that they're not overlapping. But that's basically what you wanted, right? If you knew that, you kind of like solved the problem. A little bit about as with everything else, it's
It's hard. Do you change the kind of particular tuning parameters of the MCMC algorithm between doing just normal canonical sampling and doing?
Yes, because if I'm just doing, there'll be a maximum displacement of a bead that is optimal at one temperature. But if I'm doing multi-canonical sampling, I don't want to be changing that displacement as I go up and down the energy scale, because then I'm breaking detail balance. So you end up being some miserable compromise of maximum displacement that's equally bad at low and high temperature.
Actually, along those lines, I mean, do you expect your sampling problem, or maybe that optimal parameter, to change as you tune the histogram? So would it ever make sense to tune the step size?
So, well, actually, I'm printing out something that will answer that question, I think. There you go. So in the first iteration, when I had no bias, I was accepting about 60% of my moves with that one parameter. It's gone down at the next iteration. It's gone back up at the next iteration.
So it's actually getting better.
It's actually getting a bit better, yeah. I mean, that's not by design. That's just, coincidence. I've just picked a number that seemed about right. But it does, it obviously does change.
So you estimate this is probably trivial. You estimate you with the samples from every iteration of every run that you do, right?
Well, that's quite an important point as well. Is I'm estimating the V with the samples I got at the last iteration. Yeah. I'm not using the samples from the previous iterations.
Maybe I'm
just at the last, not the ones further back.
Yeah, not the ones that were generated with the older bias. Yeah, I'm only using the samples generated with the most recent bias to come up with the new bias. Yeah.
You hope that's like the best one.
Exactly. Yeah.
Or you escape, like you don't want to go full errand, right? Like you start looking something in the first round, and if it was incorrect, you just keep compounding. Sort of.
And again, that's you hope that doesn't happen if you have a long enough interval between updates. That's quite an important point because the last method we're going to look at throws nothing away. It uses every sample from sample 1 to the last sample in constructing the statistics.
I guess there's a way of down weighting, sort of.
Yeah, I mean, you could say I generate in the first iteration. I have these samples that were generated with this bias, and then I know how to reweight those to the new bias that I've got at the last iteration. You could try and make use of them in that way.
Does this also work well for, say, a first order phase transition where you really have two kind of bulk?
Yeah. This is exactly what this method's for. Really, is first order. Obviously, we're a long way from first order with 7 beads, but
you made the system a lot
yeah, that's where I normally use it. In fact, what I spend most of my time doing is multi-canonical sampling in the context of where I've got two energy modes separated by a very large barrier. And we do these phase switch methods. So we introduce a Monte Carlo move that we define our microstates relative to the minimum of the mode. And then we have a Monte Carlo move that just swaps the minimum. And you will never accept that move unless you do some multi-canonical bias to make you accept that move. So then you're not having to sample all of the mixed phase information in between. You're just going straight from one phase to the other phase.
But to make that work, you needed this bias.
You need a bias, yeah. And that works really well if you're going between 2 different crystalline configurations, because then you don't have to melt and refreeze to get into the other configuration.
So that's you have a problem where you already.
So I've got two modes.
You know.
I know the modes very well because they're 2 crystal structures. So I know this one's FCC, this one's BCC, or this one's diamond, this one's hexagonal diamond. I know exactly where the minimum of that mode is, or the maximum if I'm talking about probability. So I define my microstate coordinates relative to that minimum. And then I've got a Monte Carlo move that just shifts the origin, shifts which minimum I'm taking as the origin. So it takes me in one move from one crystal structure to the other. You would never accept that in a million years. But with the multi-canonical sampling, you can say, I want flat sampling over some order parameter that distinguishes between the 2 minima in that augmented space. So I can get flat sampling, reweight it, and I can tell you at any hyperparameter what is the relative population of those 2 modes.
There are definitely a lot of variations on the same
Yeah.
theme as you put it.
So I guess this also relies on the energy being a good collective variable in the sense of what Pierre was saying yesterday.
Yes.
And then so if you have a diagram like what you drew where you have 2 modes, but it's not in the energy direction, does this still cause you problems?
Well, it doesn't cause me problems because I know that I can just do this, right? That's what I'm doing, is I'm going through higher energy states. Yes, if I was just trying to, if I was at low temperature and I was trying to bias something to get me from here to here, I'd be in trouble unless it was that.
Right.
Yeah.
So it's important that somewhere at higher energies maybe you have a connection between all of them.
Yeah. So there are paths. Yeah. Although having said that biasing that wouldn't get me anywhere either, unless I'm doing clever moves that allow me to break and reform bonds. Otherwise, I'm just going to pile up the bias, and I'm going to be, pushing atoms through each other in order to get between the 2 minima.
Yeah. Thanks.
I'm going to refresh my water, I think, before I carry on.
But it's not really in the way we
Alps.
The other way around,
Colder.
The mode, location.
So what I like,
And the whole idea is that
some other guy.
if you anneal further,
Yeah.
You're still mic'd up, so
Oh,
don't
right.
say anything grossly offensive.
This isn't the first I've got away from a lecture room without being mic'd up. I've got halfway across campus before.
I mean, I can
Sorry? Well, so this is sort of the physics staff common room. I mean, if you need a guest mug, I can provide you with a guest mug.
If it's possible.
Maybe. No. Yeah, there might be some plastic cups somewhere. I don't know if we.
yeah, a mug or a cup.
Oh, there's a.
Water.
Help yourself to a wine glass. There you go.
Yeah, microphone's still on.
I know.
I don't care.
Yeah, I'm not saying anything controversial. Hello, online people.
It works really well as a Jupyter notebook.
Mm.
Nice. I'd never thought of doing that.
And with that, then you can
Makes a lot of sense for something like this. So how you do a lot of your lectures?
I know. I know.